Rotating rod. We have a wooden rod of mass M and length L, and it's placed on a frictionless axle up here that passes through its top end. A small piece of clay is fired with an initial velocity v0 into the exact center of the rod. The piece of clay strikes the rod and sticks to it. And what's going to happen is this entire rod will pivot on the axle and will rotate like that. So what is the linear momentum of the piece of clay? Then a couple questions about the linear and angular momentum of the clay rod system after the collision. Are they conserved? Then find the angular velocity of the clay rod system and find the maximum angular displacement of the clay rod system after the collision. What is the linear momentum of the piece of clay? Well, believe it or not, it's this simple. It's just P0 is mv0. And sometimes your APC free response questions will be that easy. So if you look at a question and you get very scared by all the words, don't. Because sometimes the first couple parts are pretty straightforward and you can get points for that. And a point for this problem, or 2 points, well, probably just a point, that counts the same as a point for something way more complicated. So please don't lose faith once you look at the question. See if there's something very easy you can pick out of it. Is the linear momentum of the clay rod system conserved after the collision? Explain. No. Why? There is an external force. Where? Okay, this is not the external force. This is part of the system, the clay and the rod, but look at this axle up here. That is exerting an external force on the system. So as the system tries to move, if it tried to translate to the right, it can't because of that axle. So if you have an external force, the sum of the forces is not equal to 0, and your linear momentum is not conserved. Is the angular momentum of the clay rod system conserved? Well, don't get confused. Don't say, well, here's a force, so no, it can't be conserved. But what is this rod rotating about? This axle right here. So you have a force applied to the axle. So your line of action to your axis of rotation there, your line of action is equal to 0, the magnitude, so there is no torque. Whenever you exert a force at your axis of rotation, it provides no torque. So since the sum of the torques is equal to 0, angular momentum is conserved. What is the angular velocity of the clay rod system after the collision? We've been giving a hint here because of all the questions about conservation of momentum. And since angular momentum is conserved, your initial will equal your final angular momentum. And that's right down here. So what is the initial angular momentum? That may seem a strange question because you have this piece of clay moving in a straight direction. But we want to find the angular momentum about this point. So when we construct our picture over here, we find out that the clay does have an angular momentum about that point, even though it's moving in a straight line. Here's the equation. It's the magnitude of r cross p, where r is the vector between where the clay is and where this axle is. And then we put in the numbers here. We have r sine theta. Okay, that's your r cross p term. And you have mv0 for p. And note, r sine theta is this distance here. Okay, that's the projection of r onto a vertical line, the line of action, connecting the axis of rotation and where my motion is over here. So here's your line of action. Okay, so we note over here where we have our r mv0 sine theta, which is just the definition of the cross product magnitude, we see that r sine theta is L over 2. So right here, this is our initial angular momentum. And let's just cross this so you can kind of look at it. And just to quickly review, don't want to erase, want to write. This is our definition for a cross product, finding the magnitude. It's just the sine of the angle between r and momentum. And then when we construct the picture, we notice that r sine theta is L over 2, as the clay is striking the rod right in the middle. So we come up with this very simple expression for the angular momentum. Using the conservation of angular momentum, we have L0 is equal to I omega final, right? Because we want to find omega final. So we divide through, and we find omega final is our initial angular momentum over the moment of inertia. Well, here's our initial angular momentum calculated previously, and now our moment of inertia. It's certainly equal to 1/3 ml squared because that is the moment of inertia of the rod about its end point. R is just the length of the rod, so we substitute L there. And sorry about we're using L for the length. Please don't confuse it with angular momentum. There's no subscript on it, so hopefully it'll be clear. We also have the moment of inertia of the clay. Right? The clay is now stuck here and is rotating. We're treating it as a point particle, so that moment of inertia will just be mr squared, where r is the distance between the clay and the axis of rotation, which in this case is L/2. So we substitute that in. Then we just do some algebra, multiply through, cancel like terms, etc. And we have omega f is equal to this term right here. So please follow that algebra and work it out on your own sheet of paper, please. To find the maximum angular displacement, that will be as the rod rotates up to a point here where it stops moving. Right? That's its maximum angular displacement, theta. So we're going to use conservation of total mechanical energy, where the rotational kinetic energy after the collision is totally transformed into gravitational potential energy when the rod reaches its maximum angular displacement when omega is equal to 0. There is no translational kinetic energy since the rod is not moving in a linear direction, it's just rotating. And we're going to be using this little math diagram to help us figure this out. Doing a bit of geometry and trigonometry here, we have this length L, the rod rotates up theta, and we can draw a triangle right here which shows that that piece is L cosine theta. Now the total length of the rod, of course, is L, so this little piece here, which is how much the rod goes up, is L minus L cosine theta. So please review that, and here let me make it a little easier for you to see. So you might think, okay, the rod goes up a distance h, but it really doesn't. Well, the rod, let's see what goes up h. The end certainly goes up h. This point here doesn't go up at all. And then we have a line here. This rod is a line, so at the center of mass of the rod, this piece goes up h/2. And we have to deal with the center of mass here because we have an extended body. So the height that we're going to use for the gravitational potential energy will be h/2, or L minus L cosine theta, that entire expression, divided by 2. That's a big difference from dealing with extended bodies and just point masses. Our final gravitational potential energy, when the rod gets to the top right as it stops and before it starts falling down, will be 1/2 mgh. Okay, here's our h term, but we said the center of mass only goes up h/2, so that takes into account the height. Here's a total mass. Make sure you add the mass of the clay, and here's g. So that is our final gravitational potential energy. Now we need to find the initial kinetic energy, which, as we just said, was all rotational kinetic energy, as the rod is rotating and not translating, and translating means linear. Calculating the rotational kinetic energy, it is 1/2 I omega squared. Here's our value of the moment of inertia found earlier, and here is our omega, and then we have to square it. So first, we square the term on the right, and we come up with this expression here, okay? And notice we didn't multiply this out in the denominator. Why? Because we noticed the similarity, maybe it did, between the first term and one of these terms. And the way to make that similarity more evident is we're going to factor out a 2 in the denominator from here. So we have 1/4, and then we're going to have 2/3 capital ML squared plus 1/2 little m times L squared. And look at that. That matches one of these guys over here. Here's what we have from the previous slide, where we had squared this term, and then there was an L squared right in front of there, and we just put that over in this right here. And now, look what we have. This term is the exact same as this, so they cancel out. And we now have our rotational kinetic energy is this. So now we use conservation of total mechanical energy, where we have our gravitational potential energy at the top, where it's not moving, so there's no kinetic energy, and that equals the kinetic energy rotational at the bottom, where there was no gravitational potential energy. Now right about now you should be complaining, hey, this is kind of unfair. How did you know to do all this kind of work? Well, because I've done it several times, and you kind of see the trick after a bunch of times working it. So the practical thing, if you're taking this on an AP exam and you just can't see the trick there, leave the work you have, set up the equations, and then move on to something else. You may not have time to go through all this algebra. We now finish up the algebra. We've got this expression from the previous slide. We divide both sides by capital M plus little m. We have it over here too, so that now becomes squared. A little more rearranging. And then our maximum angular displacement is this expression right here.